You want to be great.
Okay, looks like we had some audio problems on our recording last time, so hopefully that clicking I did just fixed it for us for this time. But if not, just so you know, we also have last year's recordings available if we have any more audio trouble today. Or maybe you haven't looked at Friday's lecture yet, but got a couple notes, so we're trying to workshop that. Okay, so when we left off last time, we were talking about relationships between flow and pressure and resistance. So I have a short little question for you here, just about flow and pressure. So you may have seen this image come up on the slide before. Well, let's jog our memories before we break into blood vessels, not physically, just, conceptually. So in these questions, we're just looking at opposite ends of a tube. So we're looking at A versus B. Currently, we're starting out with A at 100, B at 50. So hopefully we can predict from this the direction of flow. That's not one of the questions I asked you, but you should know that we're going from areas of high pressure, so from A, to areas of low pressure, to B. So that's how our gradient would work here. Our pressure gradient is what drives our flow. So after we figure that out, we're thinking about what happens as we start to change some of these properties. So what I've asked you to begin with is to think about what's going to happen to the flow if we increase the pressure at A. Okay. So if we're increasing the pressure at A, looking for something just really basic here, not actual real math, right? We're just thinking about the fact if we turn this faucet on harder, essentially, we increase this pressure at A, our flow is going to increase. We want to conceptually, mentally relate that to our flow rule. So remember that flow is equivalent to our difference in pressure divided by our resistance. Okay, so what we've done here is we've increased this difference in pressure. Right, so instead of 100 minus 50, we now have 150 minus 50. So this difference in pressure has gone up. So our flow has gone up. So hopefully the example is easy to sort of intuit, and hopefully that helps you kind of tie back to this more abstract kind of equation form. Okay. So for our second question, they both increase by 50. Right, so what we're talking about here is a little trickier, right? So we have increased the pressure at A, right? So we're taking A from 100 to 150, right? So we have greater pressure. So initially, we might think that this is just the same as the first example, right? We might think that this would be an increase in flow. But as we remember that flow equation, right? That flow is not dependent on the absolute pressure, but on that difference in pressure. right? That triangle is the difference, that delta is the difference in pressure. So if we increase the pressure at both ends, we essentially have not changed the difference, so our flow will remain the same. Questions about this? So we are going to go ahead and move forward. This is where we left off last time. So we had looked at different pieces of that equation for flow. And so that was just a little practice about the difference in pressure. We'll continue to practice that, and we'll add in some reviews to allow us to practice our changes to resistance as we move forward. That's going to be really important. Okay. So our main equation that we're remembering is just that flow is equivalent to the difference in pressure divided by the resistance. But when we think about physiology, we're thinking about a body. We don't have to be that super general, so we can start to substitute in properties we could measure in a person. So actually, when we're talking about flow, when we're talking about blood flow, very interestingly, blood flow is going to be the same thing as cardiac output, right? The amount of blood coming out of your heart per minute. That is what we're talking about when we're talking about flow in our cardiovascular system. Okay. Now, I'm going to put in some things, right? So I'm not going to rewrite that flow equation right now, right? But we're talking about cardiac output. I'm going to dive into that delta P. So before we saw that difference in pressure, we're talking about the fact that difference in pressure for our cardiovascular system is the difference between the pressure coming out of the heart, which was our mean arterial pressure. Okay, so our delta P in our previous lecture was our mean arterial pressure minus the other end, right? Because it's a difference in pressure. So minus our central venous pressure. Okay. And I'm pointing that out to you because there's been a little bit of an abbreviation here on this slide, because the central venous pressure coming back into the heart is so low compared to our mean arterial pressure that for our purposes, when we're talking about the cardiovascular system, it's not that it doesn't matter that we have a delta P, but this is so low, it's essentially zero. So if you subtract zero from something, you don't have to think about it. So unless we see changes to central venous pressure for the cardiovascular system, we can essentially ignore that component. So that's why over here, we see that our delta P, our difference in pressure, is just listed as our mean arterial pressure. Because it's mean arterial pressure minus, I think central venous pressure is about 2 millimeters of mercury. So essentially zero. So we got rid of it for our general purposes, since we're not really doing very specific math here. Okay. So that, then our resistance is going to be our total peripheral resistance. We'll talk a lot about peripheral resistance as we move forward, but that's essentially the drag, the resistance, the sort of blockage coming from our blood vessels, largely our arterioles. And a lot of that has to do with how narrow, how constricted those arterioles get. Okay, so we can start to reshape this equation using some of these properties. So I'll click here. Okay, so we had our flow is cardiac output. Okay, cardiac output equal to our delta P. So that's where we're going to put in our mean arterial pressure. Okay. And for right now, we're just crossing out the central venous pressure because we're under a normal condition. It's basically zero, so we can ignore it. So mean arterial pressure divided by our total peripheral resistance is our physiological measure of resistance here, so TPR. Okay. Cool. So these are things that we will think about in detail, how they're intertwined. So they all go back to this original flow rule. But what we're going to realize as we go through this unit, right? Cardiac output we've talked about as affects the heart, right? The blood you're pumping out. Mean arterial pressure is essentially kind of like an averaged blood pressure. And our total peripheral resistance says something about that constriction of blood vessels. So this flow rule is what leads to this relationship between how much blood your heart is pumping, your blood pressure, and the state of your blood vessels. Okay. So we can get there thinking slowly, starting with the flow rule, and get to this interrelationship, and then think about, okay, how are changes in the arterioles or this peripheral resistance going to affect your cardiac output, going to affect your blood pressure, things like that. But all of those rules are just reshaping of this original basic law of physics, essentially. So we will continue to talk about that as it becomes relevant and as we vary these different properties. But for now, we are going to break into talking about our blood vessels. So go ahead and switch over and talk about our arteries and our arterioles first. So what we're moving through for the next couple of days is we're trying to understand the structure and function of all our various types of blood vessels, okay? Right. And one of the things we're paying attention to, so we're trying to pair up their anatomical differences, so like how big they are, what they're made of, things like that, to their physiological differences. So how do they function? How do they affect resistance? How do they affect flow? Things like that. So we're going to be trying to pair these two things together as we think about the vasculature. All right. So as we're talking about the vasculature, actually, I'm going to pull this up. We've drawn this before, but I just want us to draw, or I will at least draw, the order that we're going through our blood vessels. All right. So I'm going to start. I'll have the heart. I love drawing hearts. Okay. Our chambers. Okay. So as we're moving away from the heart, we're going to have our arteries. Okay. So arteries first. Okay. And then next, think in your mind before I say it, right? Okay. So next, after the arteries, we're going to move down in size. So next, we're going to have a smaller structure. The next part of the name of this PowerPoint are arterioles. Okay. We will talk about an intermediate structure, but the next really important thing we're going to talk about are our capillaries. So you will have a different PowerPoint on those, where our site of exchange is. So capillaries are going to happen in capillary beds. And then we're going to begin returning to the heart. So we're going to start with a smaller structure and build up to a larger structure, just like with the arteries, we had a larger structure and went smaller. So we're building back up in size. So we're going to have our venules. Blue. Venules. Okay. And then going back to the heart, we're going to have our veins. So that's our overall structure. So those are all the different parts of the cardiovascular system here that we'll be walking through. We'll add on lymphatics at the end, slightly different structure, slightly different system, but kind of related to this. Okay. So we're starting up at the top here with the vessels that are leaving the heart, those arteries and arterioles. Okay. So arteries are defined as blood vessels that carry blood away from the heart. So arteries are going to be big enough that you can see them. So it's going away from the heart, carrying blood away from the heart. You can see it, it's an artery. Okay. The arteries have specific properties. So if we look at their walls, we are going to see that they do have different layers. So we're going to have this outer layer of connective tissue. We're going to have a layer of smooth muscle. And then we'll have an inner layer of endothelium. Okay. So one of the special features of the arteries is that they're going to be highly elastic. That's one thing you hopefully have noticed in lab. If not, take a look at it this semester, right? And you're trying to tell an artery versus a vein. One of the things you try to do is kind of squeeze it and see how bouncy it is, that elasticity. is one of the special properties of arteries. They are also muscular. They can change their diameter. Then we get down into the microcirculation. So microcirculation, you can't really see. You're not going to see it. So this is when we get our smaller arterioles, where we will be talking a lot about changes to resistance in the arterioles. Okay, so we can see that they have a similar structure to the arteries, but they are much smaller, right? The average internal diameter of our artery is about 4 millimeters. The average internal diameter of these arterioles is 0.03 millimeters. They're small. Okay. They also have a layer of smooth muscle. This is going to be important for how they change diameter and therefore change radius and resistance. Okay. This well innervated part, they have nerves going to them. It's also going to be very related to that fact that we can change the diameter and therefore the radius of our arterioles in order to change resistance and flow. So those arterioles are leading into capillary beds, which you'll notice will look different. Right. So they are going to have much thinner walls. And this is important for us because those thin walls are more permeable. They allow things to permeate, to pass through. Right. So the capillaries are going to be our site of exchange between our tissue and our blood. Then we build back up. So our venules start to get larger than capillaries, but now we're moving back towards the heart. They're relatively thin-walled. A difference between the arteries and the arterioles is while they may have some smooth muscle, it's not really a significant component here in our venules. And then our veins, returning blood to the heart, we're going to see that they are thin-walled compared to the arteries. They have some muscle, distinguishing them from these venules. What we're going to see is they're really good at like holding a lot of volume. Conceptually, as we think about our arteries versus our veins, we're going to want to think about, we'll think in technical terms, scientific terms about compliance. But essentially, when we're thinking about arteries, we want to think about the fact that they're like hard to stretch out, but they're going to be like really strong and hold a lot of pressure there. Our veins, we're going to be thinking of as big and floppy, meaning that they can hold like a lot of volume of blood in them without really straining much. That's going to be our sort of conceptual idea of what these look like. So as you're going through the bodies this semester, maybe pay a little attention to the texture qualities that differ between those arteries and veins to kind of sort of cement that in your minds. Okay. So we'll talk about the walls in detail now, right? So when we're looking at the wall of a blood vessel, every blood vessel is going to have a layer of endothelial cells. So endothelial cells are just this inner part. So they're usually drawn here in yellow for us. So this little yellow layer here is our endothelium. Okay, so that's what's going to be touching the blood plasma, essentially, is that endothelium. It's just like the opposite of like the epithelium that we talked about when we talked on like the first day of A&P 1 about like the skin and stuff. Epithelium on the outside, endothelium on the inside of our blood vessel here. So that's our endothelial lining. The other components of the blood vessels are somewhat variable, as we just saw a little bit of in that chart, but we're going to have some variable layer of smooth muscle. Right. Whether there is some, how thick it is going to vary depending on what blood vessels we're talking about. Okay, so smooth muscle, it's the type of muscle we didn't focus much on in A&P 1, but we know about muscle. We have our 3 types, skeletal, cardiac, and smooth. So here's where we're really going to be thinking about smooth muscle. So one thing we already know about it, hopefully, is that it's going to be under involuntary control, right? The only type of muscle we were voluntarily controlling was our skeletal muscle. So your named muscles like your biceps. So smooth muscle is going to be different. So this is going to be under all sorts of internal imperceptible control systems. Okay. And then we're going to have connective tissue layers. So here they're just in beige on the outside. They can include different components. They can have fibrous parts. They will have really both of these parts. Fibrous parts kind of for structure. So the typical part of this is collagen, is the molecule providing this sort of fibrous structure. Then there's an elastic part made of something called elastin. So both of those are in the sort of connective tissue layer on the outside. Okay, so we're going to start talking about the arteries. So we're basically just going through blood flow in order in this class. We talked about the heart before. Now we're talking about the arteries going away from the heart. Okay. So the artery's job is essentially to be a transport pathway, and we want them to get blood out there pretty quick, right? You've just oxygenated this blood in the lungs. You're sending it out to the body. You want the blood to get where it's going as fast as possible. So our arteries are going to be relatively large in diameter, right? They're large in diameter because we know that when something is large in diameter, it has low resistance, right? Our resistance, I'm not writing out our whole equation, right? But our resistance, big R, was inversely proportional to radius. Actually, I think it's to radius to the fourth, something like that, right? Inversely proportional. So if you increase radius, you decrease resistance, right? So if we have a large diameter is just twice radius, right? Right. You don't need to memorize that for me, right? But like when we talk about something in terms of diameter, just think about the radius. They're the same thing functionally for our purposes. And so large diameter is going to create low resistance. If we have low resistance, right, I'm going to write this over and over and over, right? Low resistance. If you divide by a little number, right, a low resistance, you're going to get a big flow rate, right? So that's why it's important that we have low resistance here. Lots of flow. So the walls of our arteries are going to contain elastic and fibrous tissue. That's a property that is particularly true of the arteries. Arteries are under high pressure because they are getting the full blast of that pressure coming out of the heart, right? So your heart is squeezing out all of its cardiac output, right? Well, it's squeezing out stroke volume. Per minute, we have a cardiac output, and it's all going into the aorta, okay? So those walls have to be strong in order to not totally break in response to that pressure, in response to essentially that fire hose coming from the heart. So they're under high pressure, so they contain walls made of thick portions of elastic and fibrous tissue to withstand that pressure. Okay. As we move through our arteries, there are arteries and arteries, right? Some arteries are bigger than others. You've seen that in lab. When we get down to the level of our muscular arteries, they're going to be smaller. So our really small arteries might be like 0.1 millimeters in diameter. They're going to have less elastin. And that's when we're going to sort of start to control their radius with smooth muscle. But that's really going to be the most major. When you talk about regulation of radius, we're going to focus on that mostly in the arterioles. Just letting you know now that it is true of some of our small arteries. That's why it's here, kind of. Okay. So we're going to think about this pressure in the arteries a little bit more. So when we're talking about the heart, we talked about the fact that the heart is pumping blood into the aorta. This creates pressure in the aorta, which is one of the things our heart has to fight against in order to get blood into the cardiovascular system. So now we are looking at that aorta again. We're thinking about the fact that this elastic property of the walls of the aorta means that it's acting as a pressure reservoir. So that is now important for the rest of the cardiovascular system as well. So we see here, pretty sure we've seen this image before, but we'll run through it again, okay? So we're coming from the heart, coming from the left ventricle. We have our flow when our pressure in our left ventricle is greater than pressure in the aorta. You can open our aortic valves and it goes in here. As the blood is going in, it pushes out on the walls of the aorta, expanding them. All right, so we're expanding these walls here. All right, so some of it is continuing at this point to the systemic organs, so to the rest of your body. Okay. But It's really important that we have expanded these walls in this way, because when we go into diastole, right, so when our heart relaxes, we no longer have blood coming out of the left ventricle, right? We can see these aortic semilunar valves are closed now, they're shut, but we do still want flow to our systemic organs, right? We do not want like random pulses of blood going out to all the organs in your body. We really want a consistent supply of, especially oxygen, but other nutrients. We want to have a consistent way to get rid of our waste products. It's important that your blood is flowing all the time, not just some of the time, okay? So what's happening during diastole is that we're taking this pressure, essentially, has been stored in the stretch of the blood vessel walls. So they're like a balloon, right? Like if you, I should have brought a balloon actually. If you blow up a balloon, right, the walls expand, right? They're stretching. What they're really doing is kind of storing pressure, which you can tell because when you release the balloon, the walls collapse, the air comes back out. So the arteries are working the same way. So in diastole, when we don't have more blood coming in, we have recoil from the walls, which pushes that blood back in and means that we continue to have flow out to our body. So it's really important that these arteries can act as a pressure reservoir. Okay. So part of that is a summary of what we did when we were, or what we briefly talked about when we were talking about the heart. But now we're focusing a little more on the arteries. So now we want to think about the fact that that ability to hold pressure, to act as a pressure reservoir, is because the arteries have these thick elastic walls, right? So it is that connective tissue layer and its properties that allows the arteries to behave like this. If you put high pressure blood into a vein, it would not do this because its walls are different. It's not designed for this. Okay, so those thick elastic arterial walls are what allow us to do this. Okay. So we refer to part of what's going on here. We refer to the arteries as having low compliance. And compliance is just a measurement of the relationship between volume and pressure. So what we really do mean when we say low compliance here is that ability to store pressure. Okay. So storing a lot of pressure as we have these volume changes is low compliance. When we get to the veins, we'll see that they have high compliance. They can't do this. They can't have a lot of pressure like this. What they're going to be able to do is have a lot of volume. So we will compare these as we move forward, and we'll dive in a little deeper on that compliance. Okay. So these blood vessels are expanding during systole. Systole is the part where we're squeezing the heart, pumping out the blood. And then the blood vessels recoil, bounce back, get smaller during diastole in order to continue to push blood forward. Okay. So when we're thinking about compliance, right, so compliance is a measure of how a blood vessel changes in response to a change in volume. Part of why I didn't phrase it exactly this way when I was telling it to you on the last slide is I think it takes a while staring at these definitions and thinking about them over and over to kind of internalize what we're talking about with pressure and volume here. So you will be set if you remember that arteries have low compliance and hold high pressure, and veins do the opposite. They have high compliance and lots of volume. But technically what we're talking about here with compliance is that when we have low compliance, what we're saying is putting just a little bit of blood, a little bit of extra blood into that artery creates a massive change in pressure. Okay, so that's what low compliance means. What high compliance means is you can put lots and lots of blood in there and the pressure is not going to change very much. So if we're thinking about balloons, you can think about the artery as like a water balloon, right? It's really hard to blow into. It's even kind of hard to fill from a faucet, right? Because there's a lot of increase in pressure in that balloon as you try to fill it, even if you're just trying to put a tiny little bit. But if you think about like a big foil balloon, right? Like not the elasticy kind, just those like crinkly kind that make that sound. You think about trying to blow into one of those, it's not going to be very hard, right? Because you're not having to stretch those walls. You're not seeing much of a difference in pressure on the inside of a big foil balloon as you put more air in. So that property would be considered high compliance. You need to put a lot of volume in order to have a larger increase in pressure. So when we measure pressure, we're usually trying to estimate the pressure in the aorta. So the pressure is going to vary with the cardiac cycle. Okay. So the maximum amount of pressure we can have in the aorta is going to happen as we are pumping blood into the aorta, right? So we pump blood into the aorta during that ventricular ejection phase of the cardiac cycle, during systole. So now that we are into the blood vessel part of the cardiovascular system, we're just going to be thinking about systole, heart squeezing, diastole, heart relaxing, rather than those numbered phases of the cardiac cycle. We're kind of past that part. Okay, so systole, heart squeezing, that is when we have our maximum pressure in the aorta because of the ejection of blood. Our minimum pressure, our diastolic pressure, the relaxed pressure is happening when our heart is relaxed, so when our heart is filling. But because these walls expanded during systole as blood was pumping into the aorta and are now recoiling, it's not zero. The pressure in your aorta should never be zero. And that pressure, that lower pressure, is going to be your diastolic blood pressure. So if you think about blood pressures, which we are going to think about how we measure blood pressures in just a second, these are the two numbers you're really looking for when you give a blood pressure. What people are telling you are your systolic blood pressure, the bigger number, and your diastolic blood pressure, that littler number. Okay, so hopefully neither of those is zero. That's not a good thing. Okay. So the traditional way of measuring blood pressure is not with that big machine that just tells you, although that's very nice. But we're going to think conceptually about the old school way of measuring this because it really helps us reinforce what's going on with the blood vessels, with these pressures in the arteries. And it's fun to do too. Okay. So traditionally, we measure blood pressure with a blood pressure cuff and a sphygmomanometer, which is our little pressure sensor. And we're also listening, like with a stethoscope, listening for sounds. Okay. So what we're trying to do when we measure blood pressure is we're trying to get that systolic pressure and that diastolic pressure, right? We want to know what is the highest pressure in our arteries, what is the lowest pressure in our arteries, okay? So in order to do that, what we're doing is with that blood pressure cuff, the reason we're trying to get it to squeeze so tight is we are actually trying to put so much pressure on your arm that we collapse the artery. We're trying to collapse it because when we collapse it, we know that we've put more pressure on your arm than your blood can push against, right? So that's what we're doing. And then we slowly release that pressure so that we can figure out, okay, what is the pressure in the blood vessel that is going to be greater than this pressure we're exerting on the arm with our blood pressure cuff. Okay. So we've compressed the artery with a blood pressure cuff. And then as we release pressure in the blood pressure cuff, we're listening for sounds. Okay. So sounds in the body are usually produced by turbulent flow. So think of waves crashing on a beach, right? Something not smooth, blood kind of sloshing around. So the first sound we're going to hear is something called the Korotkov sound. That's our first blood pressure. So the first noise you hear is going to happen when you hit the systolic blood pressure. Okay. So backing up, we put a lot of pressure in the blood pressure cuff. In the pressure cuff, right? More than there is in your blood vessels. We're slowly releasing it. And then eventually we hit a pressure where sometimes the blood vessels have enough pressure to overcome that. We continue to release pressure after that. And what we're listening for now is when are we not messing with blood flow at all? So laminar flow, lamina is like a sheet. So we're just thinking about like a smooth, totally smooth flow of blood. That doesn't make a sound, okay? So what we're listening to after we start to hear sound is when does our sound stop? Because when our sound stops, that means now the blood pressure in that blood vessel is greater than the blood pressure in the cuff all the time, including at its lowest pressure during diastole. So that's when we would record our second number, our diastolic blood pressure. We're also going to look through this in picture form and graph form. Okay. So here we're looking at the events in blood pressure measurement. So in our blue line, or purple line, whatever it is. So we see our blood pressure or our pressure in the cuff, and we're just smoothly releasing that. Right, so this is just a nice steady decrease as you physically are releasing pressure from that cuff. And what's happening in the artery is in the green line. So this is showing you the difference in blood pressure in systole and diastole during the cardiac cycle, essentially. Right, so we're having peaks of blood pressure as our heart is pumping out. And then we're having dips in pressure as your heart is relaxing and all our pressure remaining is just coming from that elastic recoil. And that's just happening on a cycle, right? So we can see that's happening on a cycle. And so what we're listening for are these intersection points between the pressure in the cuff, what we hear, and these pressures in your blood vessel. Okay, so we're going to take this piece by piece. Okay. So when we start out, right, so we're starting out with really high pressure in our cuff. We've deliberately pumped enough pressure into the cuff that we have compressed that blood vessel. No blood is going through it. And that's important because otherwise we wouldn't be able to get our top measurement, okay? So we have high pressure in the cuff, higher than any of our blood pressures, okay? So we've compressed this. We've squeezed it down. You can see the squeezing has really slammed that radius shut here, the radius of this blood vessel, I should say. Okay. And we're listening here below. Should note you're listening below the cuff, because if you were listening above, you'd be hearing the uncompressed blood vessel, right? It wouldn't help you. So you got to listen below because this is what you cut off. Okay, cool. So we have no blood flow, no sound. Now, we start to hear sounds here when our highest pressure, our systolic pressure, hits the same pressure as the pressure in the cuff, right? So at this point, what happens is when this pressure is at the same or maybe a little bit higher pressure than in the cuff, some blood is able to get through, but it's turbulent, it's swooshing around, it's not smooth. And you can see that actually, right, after you're at the systolic pressure, right, your pressure in the cuff is still higher than most of the other parts of the cycle here, right? So kind of we're having this opening and closing as well of the blood vessel, right? So it's going to be open some of the time when we have a pressure that's higher than the pressure in the cuff, but when we're in diastole and we're relaxing, it's closing back up again. So really everything's kind of a mess here, which is why we're hearing sounds, okay? So that's the turbulent flow. And that's why it looks like wind down here, the turbulent flow that you're hearing when you're listening with a stethoscope distal to our blood pressure cuff. That first one is the carotid cuff sound. So then we're going to continue listening until we hit laminar flow. So we can see the second point. The second point is when even our lowest pressure in the blood vessel is higher than the pressure in the cuff. So now that blood vessel just stays open the whole time, right? It's open, open, open. It's not compressed, right? So nothing is blocking it. You can see the whole cycle, all of it is higher than the pressure in the cuff. So that's when we have laminar flow. Everything's moving smoothly. We don't hear anything. So if you're taking the blood pressure, the first thing you're writing down is the highest pressure, the systolic pressure here when you start to hear sounds. And then you're listening, 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 listening until you stop hearing sounds. And that's the second number you write down. So that's how we're going to give a blood pressure. We are going to listen to a couple examples to sort of practice understanding and practice linking these ideas together in our minds. Oh, okay, examples next. Oh, well, before I give us the examples, we'll look at them. Okay. I got too excited. I like listening to blood pressure sounds is what you're really getting from the story. Okay. So when we measure our blood pressure, we're listening to these sounds, we're writing down these numbers. So our overall blood pressure that you get at the doctor is the systolic pressure, the high pressure, over the diastolic pressure, the low pressure. So I think the typical measurement is 120 over 80. Some variation from that is normal and expected, right? Preferably lower. So an example of a blood pressure might be 110 over 70. That would mean blood pressure during systole in the aorta there is 110. That lowest pressure is during diastole is 70. Okay. So we could then reshape these numbers to give us some different properties. So if we wanted to know the difference here, so the difference between our systolic pressure and our diastolic pressure is something called our pulse pressure. So our SP, our systolic pressure minus our diastolic pressure here, 110 minus 70 would give us 40 millimeters of mercury. So that's essentially the pressure that if you think about taking a pulse or radial pulse like at the base of the thumb, you think about what's the pressure hitting up at your fingers that you feel. That's the pulse pressure you'd be feeling, right? Because your baseline would be the diastolic pressure. That diastolic pressure would feel still to you. What you're just feeling is that peak above, okay? But usually when we talk about blood pressure, when we talk about like, do people need blood pressure medications, things like that, or in physiology, when we think about our homeostatic mechanisms, what we want is the overall pressure over time. We want our mean arterial pressure, MAP, which is that same number that we just plugged in as our delta P in our flow equation. So we can find that from our typical BP that we would measure in clinic as well, but we have to do a little math. It's not just the systolic pressure plus the diastolic pressure. It's going to be a weighted average. So essentially what's happening is that your heart is beating, pushing out blood, and it should be resting for more time than it's contracting, right? Your heart should be in diastole for longer. So we weight this average, and I'm going to write it out because it's a little misleading there. So we're looking at our systolic pressure. I think we should have an extra parentheses is what I'm saying. Plus twice our diastolic pressure. Okay. And then we're dividing that by 3. All right. So this is because 1/3 of the time we're in systole, then 2/3 of the time we're in diastole. So we got our average overall by adding those two things together and then dividing by 3. Okay. So quick look back to the beginning portion of this lecture. And then I think we get to listen to blood pressures. Okay, so hopefully from word recall, we could get to this one. We have not talked about valves as relates to our general arteries. The only place we see a valve is really coming out of the heart there in the aorta. Valves are going to be really important when we get to veins, but they're not really part of our arterial system. The elasticity and the low compliance make a difference for resisting pressure. The smooth muscle walls make a difference for resisting pressure. The fibrous structure makes a difference for resisting pressure. Valves are going to be solving a different problem in our venous system. Okay, good. Now we have some blood pressures. Okay, so we're going to finish off. We got one link. We're going to listen to one together and then we'll do this. Testing ourselves. I want us to listen to number 1 first. Okay, so what we're looking at, I should say, so we're pumping up a blood pressure cuff we have this little meter on our sphygmomanometer that tells us how much pressure we've put into the cuff. And so we're going to listen to them just pumping it all the way up until the blood vessel is compressed. And then we're going to be listening to those sounds as we release pressure. So we're still just filling up that blood pressure cuff. I got it nice and high. Now we're listening for sounds. Okay, so you can hear how you kind of may hear some extraneous sounds at like either end. Some of that might be from people shifting around, but hopefully you all heard that central zone where you heard like really significant like boom, boom, boom beats. That's the zone we're looking for when we're looking for our blood pressure measurements. So I'm going to take us back to that again so you can listen now that you've heard the whole thing. So hopefully as we were listening to this one, I can tell you, I think we heard something sort of around here was when we really started to hear those consistent sounds. So around like 98. And then they started to become laminar, maybe somewhere here around 64, what I would say here. So we're going to listen to then one example more. I'm not going to tell the answer to. Let's listen to number 3. Oh, and you can see we had some answer choices for you. Okay. Example 3, yeah. So got you some examples: 92 over 62, 102 over 62, or 130 over 92. And we're going to listen to that example. And you compare which one seems closest to you. Let's do it one more time just because I like looking at them. But we're going to end here for the today so you can back up. So sure you will all get further explanations in the future on how to take good blood pressures, but I think that was about a 92 over 62. I'll pick up here next time.